Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to continue with our discussion on the topic data representation in the computer. This is part 3 of a 3-part series of presentations in this topic, with the title of this presentation being binary arithmetic operations. My name is MemGM, or you can simply call me Emily Swap. In this presentation, we are going to look at how we perform various binary arithmetic operations, which include representing signed numbers, binary addition, binary subtraction, binary multiplication, binary division. Let's commence by looking at how we represent signed numbers. An integer is any whole number, whether positive or negative, that does not have a fractional part. An unsigned integer is one that is positive and not preceded by any minus or plus sign. In the decimal system, the minus sign is used to indicate that a value is negative, and an optional plus sign is used to indicate that a value is positive. Signed numbers are therefore those numbers that have been preceded by a sign, either a positive or a negative sign. Negative numbers are used to carry out subtraction in the computer's arithmetic operations. This is based on the notation that subtracting a number is the same as adding its negative to the other. The positive and negative integers are therefore collectively known as signed integers. The 4 most common methods or ways of representing signed numbers are sign and magnitude, 1's complement, 2's complement, and BCD. Let's look at sign and magnitude. This is prefixing an extra sign bit to a binary number. In the decimal number system, we can represent a negative number by placing the minus sign in front of the number. For example, -2, -3, etc. However, this is not possible in binary, as we can only have binary numbers. In sign and magnitude representation, the leftmost bit is used to represent the sign that is positive or negative, and the remaining bits represent the magnitude. The left, or this leftmost bit, is called sign bit. In binary, a negative number is represented by prefixing a digit 1 to the number, while a positive number is represented by prefixing a digit 0. For example, the computer using a 4-bit to represent a decimal number, for example, number +1, its sign bit is 0, and its magnitude is therefore 0, 0, 1. Therefore, the 4-bit binary representation of positive 1 would be 0, 0, 0, 1. While for negative 1, the 4-bit binary representation would be 1, 0, 0, 1. The range of numbers that can be represented using 4 bits is -7 to +7. To represent a number, for example, -35 using sign and magnitude representation would therefore be done as follows. Just as we learned in part 1 of 3 of this series of presentations, and part 2 of 3 in this series of presentations, we saw that for you to convert a decimal number to binary using the long division method, you continuously divide the decimal number by 2 while generating the remainders at every stage until you have a remainder of either a 1 or a 0 as the last result of the division. And therefore, when we continuously divide 35 decimal by 2, in other words, when we convert 35 into its respective binary number, we get 1, 0, 0, 0, 1, 1. That is, 35 divided by 2 is 17, remainder 1. We note down the remainder 1. Then we divide 17 again by 2, we get 8, remainder 1. We note down the remainder. Then we divide 8 by 2, we get 4, remainder 0. We note down the 0. Then we divide again 4 by 2, we get 2, remainder 0. We note down the 0. And then lastly, we divide 2 by 2, we get 1, remainder 0. And because we have ended up with 1, we then take 1 as our last remainder. And then we pick all the remainders towards the first remainder. That is 1, 0, 0, 0, 1, 1. So our binary equivalence of 35 is 1, 0, 0, 0, 1, 1 binary. But then, because we are converting -35 to binary, we then represent or add a 1 to our binary. So we add 1 bit for the sign on the most significant bit side. That is 1, 1, 0, 0, 0, 1, 1 binary. So this means that this binary represents -35 with the leftmost bit 1 representing the negative sign. In the case you are told to give, for example, an 8-bit representation of -35 using sign and magnitude representation, get the binary equivalent of 35, which is 6 bits. Then add 2 zeros to the left of the bit in order to make it an 8-bit number. For example, because we have gotten our binary equivalence of 35 being 1, 0, 0, 0, 1, 1 binary, but we are requested to represent this number in its equivalent 8 bits, then we add 2 zeros on the leftmost hand side of the number, which gives us 0, 0, 1, 0, 0, 0, 1, 1 binary. However, because we are representing negative 35, where we know that the negative sign is represented using binary 1, while positive is represented using binary 0, it means that then we need to change the leftmost bit 0 to 1 in order to represent the minus sign. And therefore, the answer to our question becomes 1, 0, 1, 0, 0, 0, 1, 1 binary. The most significant bit, 1, in this case, represents the negative sign. The problem of using this method is that 0 can be represented in 2 ways. These are, we enclose 0 in brackets, then 0, 0, 0 binary. And we can also represent the same with enclosing 1 in brackets, then 0, 0, 0, 2. In other words, depending on the system, we can represent the 0 either as 0, 0, 0, 0, or 1, 0, 0, 0. In other words, depending on the situation and the system, 0 may be represented using either a 0 or a 1. This drawback and a few others have made scientists to develop other methods of representing numbers in the computer. Let's now look at what we call one's complement, or how we use one's complement. The term complement refers to a part which together with another makes up a whole. The idea of complement is used to address the problem of signed numbers. In decimal numbers, 0 to 9, we talk of 9's complement. So, the 9's complement of 9 is 0. The 9's complement of 6 is 3. The 9's complement of 2 is 7. In other words, what is it that when we add it to 9 can generate a 9? It is 0. What is it that we add to 6? We can get a 9. That is 3. What is it that when we add to 2, it can give us 7? That which we are adding, no, let me repeat. What is it that when we add to 2 can give us 9? The answer is 7. So we are simply asking ourselves, what is it that can complement 0 to give us 9? What is it that we can complement to 3 or to 6 to give us 9? What is it that we can complement to 7 or to 2 to give us 9? That which we can complement to 0 to give us 9 is 9. That which we can complement to 3 to give us 9 is 6. That which we can complement to 7 to give us 9 is 2. In binary numbers, the one's complement is the bitwise not applied to the number. I repeat, in binary numbers, the one's complement is the bitwise not applied to the number. I know you are asking yourself, what do I mean by bitwise not? Bitwise not is a unary operator, that is an operation on only one operand that it performs logical negation on each bit. In one's complement notation, positive numbers are represented as usual in unsigned binary. However, negative numbers are represented by simply flipping all the digits. This means replacing all the zeros by ones and all the ones with zeros. This means replacing all the zeros by ones and all the ones with zeros. When converting a number to its ones complement, the number of bits must be stated. For example, what is the 8-bit ones complement of 1, 0, 0, 0, 1, 1 binary? What is the 8-bit ones complement of 1, 0, 0, 0, 1, 1 binary? How do we proceed, my dear students and the rest of the learners? This is what we do. Number 1, add 2 zeros in front of the most significant bit. And our most significant bit in this case is 1. That is the leftmost bit. So when we add 2 zeros to 8, or in front of 8, we get 0, 0, 1, 0, 0, 0, 1, 1 binary. The next step is we flip the bits. In other words, we change zeros to ones and ones to zeros. So this gives us 1, 1, 0, 1, 1, 1, 0, 0 binary. The third step now is the 8 bits ones representation then of 1, 0, 0, 0, 1, 1, therefore becomes 1, 1, 0, 1, 1, 1, 0, 0 binary. So that is the 8 bits ones complement, or ones not complement. I repeat, this becomes the 8 bits ones representation of 1, 0, 0, 0, 1, 1 binary. So at the end of the day, we can say that the ones complement of our number becomes 1, 1, 0, 1, 1, 1, 0, 0 binary. Let's now look at another question. If you are told using 7 bits, give the ones complement of negative 17, what would you do? Using 7 bits, give the ones complement of negative 17. So the solution will be, number 1, find the binary representation of 17. That means convert 17 decimal number into its equivalent binary number. My dear students and the rest of the learners, if you don't know how to convert decimal numbers to their equivalent binary number system, kindly visit EmilySwap ICT YouTube channel and look for the video by the title Data Representation in the Computer, Part 2 of 3, under Number Systems Conversions. And therefore, when we convert 17 to its equivalent binary number, we get 1, 0, 0, 0, 1. The second step is to add zeros in front of the most significant bit, which in this case is 1, to make it 7-bit number. So this gives us 0, 0, 1, 0, 0, 0, 1 binary. The third step is now to flip the bits. In other words, we now change ones to zeros and zeros to ones. This gives us 1, 1, 0, 1, 1, 1, 0 binary. Therefore, the 7-bit ones complement of negative 17 will therefore be 1, 1, 0, 1, 1, 1, 0 binary. Let's now look at 2's complement. 2's complement, equivalent to 10's complement in decimal numbers, is the most popular way of representing negative numbers in computer systems. One main problem with 1's complement is that there are 2 ways of representing a 0, just as we have seen. So, the 2 main advantages of using the 2's complement notation to represent numbers are: number 1, there is only one way of representing a 0. That is 0, 0, 0, 0. This is an improvement over 1's complement because when performing arithmetic, you don't need special circuits to deal with the 2 representations of zeros. Number 2 is that effective addition and subtraction can be done even with the numbers that are represented with a sign bit without a need for extra circuitries to examine the sign of the operand. So, the advantage or importance of ones and twos complement is that they permit the representation of negative numbers in digital systems. Therefore, my dear students and the rest of the learners, it is important to note that the ones and the twos complement is very important because this is what permits negative numbers to be represented in digital systems. And this simplifies the representation. For an n-bit word, one bit is used for sign and the remaining n-1 bits for magnitude. We can represent numbers ranging between -2 to power n-1 to 2 raised to power n-1, then -1. For an 8-bit word computer, the most negative numbers that can be represented is ranging from -2 raised to power -7 or 128, and the most positive number is 2 raised to power 7 minus 1. In other words, we can represent negative numbers ranging from -2 raised to power -7 all the way to +2 raised to power 7 minus 1 or 127. To represent a number in two's complement notation, we begin by first finding the ones complement of the number. Then we add 1 to the result. For example, if you are told, find the two's complement of the 7-bit binary number 0, 1, 1, 1, 0, 1, 1, then we proceed as follows. Number 1, we find the ones complement of 0, 1, 1, 1, 0, 1, 1. That is, we alternate or we change zeros to ones and ones to zeros. This gives us 1, 0, 0, 0, 1, 0, 0. The next step is we add 1 to the ones complement. That is 1, 0, 0, 0, 1, 0, 0 plus 1. My dear students and the rest of the learners, note that we are adding 1 on the least significant digit in our binary. That is, in this case, to 0. This gives us 1, 0, 0, 0, 1, 0, 1. Because binary digit is 0 plus 1 gives a 1. So the 2's complement of our number 0, 1, 1, 1, 0, 1, 1, therefore becomes 1, 0, 0, 0, 1, 0, 1 binary. What about if you are told, find the 2's complement of the 8-bit binary number 0, 0, 0, 0, 0, 0, 0, 0. What we do is, number 1, we find the 1's complement of the number. That is, we replace zeros with 1's. In this case, we get 1, 1, 1, 1, 1, 1, 1, 1, binary. And then we add 1 to the 1's complement. That is 1, 1, 1, 1, 1, 1, 1, 1, plus 1. Note, we add 1 on the least significant bit side. So what did we get? 1 plus 1 in binary is a 0, carry 1. So 1 plus 1 gives us 0, carry 1. That carry 1, we add it to 1. It gives us 0, carry 1. And that continues all the way to the 8th bit, where we add that carry 1 plus 1, which gives us 0, carry 1. So we carry 1. And therefore, we get our answer or our result as 1, 0, 0, 0, 0, 0, 0, 0, 0. Now, when you note at this number that we have gotten, it is no longer an 8-bit binary number. It has become a 9-bit. So, because we now have 9 bits, what we do, my dear students and the rest of the learners, is we discard the extra bit 1. That is the leftmost bit. In this case, 1, for we are working with 8 bits. Note, if you are told to find the 2's complement of an 8-bit binary number, it should never exceed, or the result should never exceed 8-bit. Any excess bit is discarded. And if they are less than 8, then it means that we have to introduce some zeros to that initial number before we proceed with finding the 1's complement. And therefore, in this case, we discard the 0. Not the 0, but the 1. We discard 1. The one I have highlighted or circled in red. That one. So when we discard it, our answer becomes 0, 0, 0, 0, 0, 0, 0, 0, binary. My dear students and the rest of the learners, when you look at this result, we are ending up with the initial number. We are ending up with our initial number, meaning the 2's complement of the 8-bit binary number consisting of series of zeros only is those zeros at the end of the day. So this discarding action, which is normally performed by the computer, is a convention that is used in 2's complement notations to maintain the original number of bits specified. And in this case, it is 8 bits. Let's see or compute another example. So using 6 bits, find the 2's complement representation of -25 decimal. So how do we proceed? Number one, we find the binary equivalent of 25. So if we continuously divide 25 by 2, we're generating the remainder using the long division method that we learned in part 2 of this series of presentations that is posted in Emily Swap ICT YouTube channel. We get 1, 1, 0, 0, 1 binary. And then we add a 0 in front of the most significant bit to make it 6-bit number. That is 0, 1, 1, 0, 0, 1 binary. So, because the binary equivalence of 25 is currently 5 bits or 5 digits, as you have seen in step 1, then before we proceed to our next move, we have to make those digits or those bits to become 6. Because you are talking about using 6 bits, find the 2's complement representation of -25 decimal. And therefore, to make them 6, our step 2 is to introduce a 0 on the most significant bit side. So we get 0, 1, 1, 0, 0, 1 binary. And then we proceed now to step 3 to find the 1's complement of 0, 1, 1, 0, 0, 1 in binary. So this means that we alternate zeros with ones and ones with zeros. In other words, we replace or we change zeros to ones and ones to zeros. So this gives us 1, 0, 0, 1, 1, 0 binary. Once you have done that, the next step is to add 1 to our 1's complement. And our 1's complement is 1, 0, 0, 1, 1, 0 binary. So when we add 1 to 1, 0, 0, 1, 1, 0, just as we have seen in my previous example, then we shall get 1, 0, 0, 1, 1, 1 binary. This is because if we add 1 to our least significant bit, which in this case is 0, we get a 1, because according to the rules of binary addition, which we are going to see in this presentation, when we add a 0 to a 1, what we get is a 1. And that's why we have now our result being 1, 0, 0, 1, 1, 1 binary. So, to convert the positive decimal numbers to binary in 2's complement, positive numbers are written with leading zeros to fill out bits to the left. That is the sign bit, followed by their usual representation. For example, positive 21 in an 8-bit word will give us 0, 0, 0, 1, 0, 1, 0, 1 binary. Why? Because the binary equivalence of 21 decimal is 1, 0, 1, 0, 1. But then because we are talking about an 8-bit, it means that we then introduce 3 zeros on the most significant side of our result, which will give us 0, 0, 0, 1, 0, 1, 0, 1. It is important to note, my dear students, and the rest of the learners, that we are adding 3 zeros to make them 8 with our 8th bit, that is the most significant bit, being a 0 to indicate that what we are representing is a positive number. And therefore, in this case, our most significant bit, that is the leftmost side bit, 0, represents the positive sign. Now, let's challenge ourselves a little through this question. Represent positive 2789 using sign and magnitude. Convert positive 2789 using sign and magnitude. My dear students and the rest of the learners, you can pause this presentation, then work on the figure given, and once you are through with computing it, then you can click and proceed with this presentation so that you can see whether you have gotten it right. Good. Let's see how you will proceed. So the first step is you convert 2789 decimal to its binary equivalence. And you do this by continuously dividing the number by 2. So you first divide 2789 by 2. You get 1391, remainder 1. You know now the remainder. Then you divide again what you have gotten by 2. That is 1394 divided by 2. You get 697. And then remainder 0. You note now the remainder. Then you proceed again by dividing 697 by 2. You get 348, remainder 1. You note down the remainder, and you continue all the way until you get your remainder or your last number in the division being either a 0 or a 1. So our last step is 2 divided by 2, that gives us 1, remainder 0. And therefore, because our least number in this division is 1, we treat 1 as our remainder. And therefore, we pick those remainders, as you can see from the arrow that I have indicated, commencing with the last remainder towards the remainder that you got at the first division. And therefore, that gives us 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1 binary. So that is the decimal equivalence of 2789. So what do we do next? So we add a 0 bit to that number we have gotten, or to that result, to represent the sign. And therefore, our answer becomes 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. So the most significant bit, 0, in this case, will indicate that this is a positive number. Let's now look at binary addition. There are 5 key rules that govern binary addition. These are: number 1, 0 plus 0 plus 0, or simply 0 added to 0 is supposed to generate a 0. 0 plus 0 equals to 0. This is the first rule. This is the same as 2 raised to power 0 times 0. Any number raised to power 0 gives a 1. So 1 times 0 is a 0, plus 2 raised to 0 times 0, which gives 0. So 1 times 0 plus 1 times 0, that is equals to, or it is the same as 0 plus 0, which gives us 0 in decimal. And it is also equivalent to 0 in binary. The second rule, if you add 0 plus 1 in binary, we get 1. So 0 plus 1 equals to 1. Now, this is the same as 2 raised to power 0 times 0, which gives us 1 times 0, plus 2 raised to 0 times 1, which is equivalent to 1 times 1. So 1 times 0 gives us 0. We add it to 1 times 1, which gives us a 1. And therefore, 0 plus 1, we get 1 in decimal, and it is also equivalent to 1 bit in binary, or 1 in binary. The third rule is, if you add, or when you are adding 1 in binary to 0 in binary, you get 1. So 1 plus 0 is equals to 1. So that is that rule. This is the same as 2 raised to power 0 times 1 plus, in bracket, 2 raised to 0 times 0, which gives us 1 times 1 plus 1 times 0. 1 times 1 is equals to 1 plus 1 times 0 equals to 0. Therefore, we get 1 plus 0, which is equals to 1 in decimal, or equals to 1 in binary. So 1 plus 0 gives us 1 in binary. The fourth rule is if you are adding 1 plus 1 in binary, what you get is 0 carry 1. My dear students, note carefully. We don't say that 1 plus 1 is equals to 1, 0. No. This number 1, 0 is read as follows: 0 carry 1, 0 carry 1. So anytime you add 1 to 1 in binary, you never get 2. There's nothing like 2 in binary. Binary is either a 0 or a 1. So if you add 1 to a 1, you get 0 carry 1. 0 carry 1. That one that you have carried, if you are adding it to a series of bits, then you add that one you have carried to the bit that is next on that order, or in that order. And therefore, 1 plus 1 equals to 0 carry 1. This is the same as 2 raised to 0 times 1 plus 2 raised to 0 times 1. This gives us 1 times 1, which is 1, plus 1 times 1 equals to 1. So that is equals to 1 plus 1. If you were to add that in decimal, if you are to add 1 plus 1 in decimal number system, that would give 2. 1 plus 1 in decimal equals to 2. But now, because we are dealing with the binary, you have to convert that to decimal to its binary equivalence. So if you convert 2 to its binary equivalence, that means you divide 2 by 2. That will give us 1. The first division will give us 1, remainder 0. And then if you divide again by 2, you'll get 1. So if you divide for the first time, 2 divided by 2, you will get 1, remainder 0. So you note down the 0. And then you move on again and divide 1 by 2. That will still give us 1. And therefore, simply put, my dear students and the rest of the learners, if you get 2 in decimal, to convert it to binary, just as we saw in my presentation part 2 of 3 in this series, you will get 0, 1. You get 0, 1 in binary. 0, 1 in binary. You get 0, 1 in binary. So which is read as, or you can read as 0, carry 1. Now the fifth rule is this. If you add 1 in binary plus 1 in binary plus 1, so if you add 1 plus 1 plus 1 in binary, what you get is 1 carry 1. 1 carry 1. This is the same as 2 raised to power 0 times 1 plus 2 raised to power 0 times 1 plus 2 raised to power 0 times 1, which gives us 1 times 1 plus 1 times 1 plus 1 times 1. That is 1 plus 1 plus 1. 1 plus 1 plus 1. In decimal, we get 3. 3 in decimal. If we convert it to its binary equivalence by continuously dividing 3 by 2 using the long division method, you will get 1, 1 in binary, 1, 1 in binary. So we read this binary as 1 carry 1. So in the rules of binary addition, if you add 3 ones, that is 1 plus 1 plus 1, what you get is 1 carry 1. 1 carry 1. And therefore, the one you have carried, if you are adding to other several bits, you add that one you have carried to the next bit or the next number or the next binary digit, and you proceed with that calculation as we are going to see in the example I'm going to give. Just remember, in the rules of binary addition, if you add 1 to a 1 to a 1, you get 1 carry 1. In fact, assuming you have already added 1 plus 1, so 1 plus 1, we saw it gives us 0 carry 1. So if you add another 1 to 0 carry 1, it simply means you get 0 plus 1, the one that you had carried, will give you 1. And therefore, the final answer will be 1 carry 1. So 0 carry 1 plus 1 gives us 1 carry 1. Always remember that when adding binary numbers, 1 plus 1 is not equals to 2 because the digit 2 is not used in binary. Similarly, when you are adding 1 plus 1 plus 1 in binary, it is not equals to 3 because 3 is not a digit used in binary. Binary only entails 2 digits, 0 and 1, and therefore the maximum digit you can have in binary is 1. Let's see an example. If you are told to find the sum of 1, 1, 1 in binary plus 1, 0 in binary, what do you get? My dear students and the rest of the learners, note that we don't read this number as 101. No, this is binary. Now do we read it as 10, the second one, because it is binary. A binary can never reach to value 10, nor can it reach 111. So we read it just as I said in my part 1 of this series of presentations and the part 2. that are already posted in Emily Swap ICT YouTube channel. We read it as 1, 1, 1 in binary plus 1, 0 in binary. So how do we proceed? So the solution is as follows. We have 1, 1, 1, then add it to 1, 0. You organize your numbers, my dear students, and the rest of the learners, as I am showing you. So you add your value at that point based on the order of bits from the least significant side towards the most significant side. So when we add, what do we get? So we get 1, 0, 0, 1. Why do we get this? On the least significant side of 1, 1, 1, we have digit 1. While for 1, 0, we have digit 0. So 1 plus 0, which are our least significant bits or digits, we get 1. So 1 plus 0 is 1. Then on the next column, we have 1 plus 1. 1 plus 1, according to the rules of binary addition, gives us 0 carry 1. So we note down our 0, and then we carry our 1. So we take our 1 and we add it to the most significant bit for 1, 1, 1. And that most significant bit is 1. So 1 bit or 1 digit 1, plus the 1 that we have carried gives us 0 carry 1. So we carry 1. And then because there's no other value to add up there, so we assume that what is preceding or what is in front of 1, 1, 1 is a 0. Whenever there is no digit indicated, we can treat that space or that gap as a 0. So 0 plus the 1 we have carried gives us 1. And therefore, our answer becomes 1, 0, 0, 1. And then we include the radix to show it is binary. And therefore, our answer becomes 1, 0, 0, 1 in binary. So the steps to arrive at the above answer are as follows. Number 1, just as I have said, first place the binary numbers one above the other, ensuring the bits with the same weighting are in the same columns. Secondly, starting from the column on the right, add the digits and write the 1 in the same column. Number 3, add the digits in the second column. That is 1 plus the 1 we have carried, which gives us a 0 carry 1. We write down the 0 in the same column and carry 1 to the next column. Number 4, add the carry to the next column's value 1, which becomes 0 carry 1. So we write down the 1 on the fourth column. Another example is this. If you are told to add together the following numbers: 1, 0, 0, 1, 1, 0, 1, binary, to 1, 1, 1, 0, 0, binary, and then to 1, 0, 1, 1, 0 in binary, How do you proceed? You are required to add 3 numbers. That is 1001101, 11100, and 10110. So this is how we proceed. My dear students and the rest of the learners, I would advise that you pause this presentation, work out this addition, and then once you are through, click on proceed so that you can be able to see whether your answer and your approach will be similar to mine. So this is what we're supposed to do. Step 1, write down the first number. That is 1001101. And then add that to the next number, which is 11100, which gives us 1, starting from the least significant bit on your right hand side. While you are moving to the left hand side, we get 1 plus 0 gives us 1. 0 plus 1, or 0 plus 0, 0 plus 0 gives us 0. 1 plus 1 is 0, carry 1. So we write down 0, we carry 1. 1 plus 1 gives us 0, carry 1. 0, carry 1, plus 1 gives us 1, carry 1. So we write down 1, we carry 1. 1 plus 0 gives us 1. So 1 plus 1 gives us 0, carry 1. So we round down 0, we carry 1. 1 plus 0 gives us 1. And then we drop down the other one, or we assume that below the upper one, on that column, we have a 0. So 1 plus 0 will give us 1. And then we add that result to the next value, which is plus 0, 1, 1, 0, which gives us 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0, that is plus nothing. There's nothing there. We assume it's a 0. So 0 plus 0 . Let me, my dear students, pause a little bit and explain this point. 1, 0. I want to repeat this step so that you can note carefully. 1, 0, 0, 1, 1, 0, 1. When we add to 1, 1, 1, 0, 0, we have gotten from the least significant side 1, 0, 0, 1, 0, 1, 1. So if we add to 8, our third value, that is our third figure, or our third number, which is 1, 0, 1, 1, 0, or from the least significant side, we have 0, 1, 1, 0, 1. What do we get? So after you have gotten in step 1, 1, 1, 0, 1, 0, 0, 1, we add it to 0, 1, 1, 0, 0, 1, 1, 0, 1. When you add that value, then what do we get? One plus 0 gives us 1. Then 0 plus 1, we get 1. Then 0 plus 1, we get 1. Then 1 plus 0, we get 1. As you can see, my dear students and the rest of the learners, it sometimes becomes very easy to make a mistake when you omit a number. Like in this case, I had omitted this digit. And if I added it, or if I added 1, 1, 0, 1, 0, 0, 1 to 0, 1, 1, 0 without this digit, which I've written in red here, it means I would have gotten the wrong answer. So you have to be very careful when adding binary numbers, because a slight mistake in either omitting a digit or altering a digit and using another one can give you an erroneous result. And therefore, my dear students, you should be very careful when adding binaries so that you don't make a mistake without your knowledge. Like in this case, if I have proceeded with the adding this result from step 1 to 0, 1, 1, 0 without this 1 here, I would have gotten the wrong answer. And therefore, as you move on with the steps of addition, always note that the number you are adding at the next step is the right number. And therefore, let's now proceed with our step 2. So, starting on the least significant bit side, we add 1 plus 0, we get 1. Then we move on to the next column. 0 plus 1 gives us 1. And then we move on to the next column where we have 0 plus 1. So 0 plus 1 is equals to 1. Then we move on to the next column where we have 1 plus 0, which gives us a 1. And then next column, we have 0 plus 1, which gives us 1. And then because there are no digits here, we can drop down this 1 and this 1. Or simply assume that below here, we have zeros. Therefore, 1 plus 0 will give you a 1. Then we move on to the other one, the last one, the most significant bit 1. So 1 plus 0 will give us a 1. So at the end of the day, our step 2 will generate the binary 1, 1, 1, 1, 1, 1, 1. It will give us that result. So how do we write it down? So the answer becomes 1, 1, 1, 1, 1, 1, 1 binary. Don't omit, never omit the radix. In this case, it is 2. Good. Let's now look at binary coded decimal addition. Binary coded decimal addition. The following is the procedure for binary coded addition. Number 1, add the two BCD numbers using rules of binary addition. My dear students and the rest of the learners, if you don't know what BCD is all about, kindly visit Emily Swap ICT YouTube channel and look for the video by the title Data Representation in the Computer, Part 1 of 3 on Introduction to Data Representation, and then you are going to get a clear understanding of binary coded decimal. So in this case, we assume that you have already listened to part 1 of 3 in this series of presentations, and you know what the BCD is all about. Once you are aware of what BCD is, then we can proceed. So the first step is you add the two BCD numbers given using rules of binary addition. Number 2, if a 4-bit sum is equal or less than 9, then it's a valid BCD number. In other words, once you have added two numbers, check if the sum you have gotten, the 4-bit sum you have gotten, is equal or less than 9. If yes, that will mean that the addition is or has generated a valid BCD number. But if a 4-bit sum is greater than 9, or if a carry out of the 4-bit group is generated, it means that what you have gotten is an invalid BCD result. So what you do in that case is you add 6, which is equivalent to binary 0, 1, 1, 0 to the 4-bit sum in order to skip the 6 invalid state and return the code to 8421 system. This is because binary code, or in BCD, we have the code being 8421, as we saw in my previous presentations or in my previous videos on this topic. Then, If a carry results when 6 is added, simply add that carry to the next 4-bit group. I will make this process very simple for you, my dear students and the rest of the learners, by using an example. For example, if you are told to find the sum of 9 and 5 using rules from BCD addition, then we proceed as follows. Or simply, if you are told, add 5 and 9 to 5 using BCD, add 9 to 5 in BCD. So, if you are asked such a question, proceed as follows. Convert each of those numbers given to its equivalent binary. So when you convert 9 to its equivalent binary, you get 1, 0, 0, 1. Then convert 5 to its equivalent binary, which gives us 1, 0, 1. But because we are talking about BCD, which should be having, or each number is supposed to be represented by a pair of 4 binary digits, then we add a 0 in front of 1, 0, 1, or on the most significant side. And therefore, we have our 5 represented as 0, 1, 0, 1. So we add the 2 binaries, 1, 0, 0, 1 plus 0, 1, 0, 1. So we proceed as follows. What do we get? 1 plus 1 gives us 0 carry 1. So we add 0 carry 1 to 0. That gives us 1. 1 plus 0 is 1. We write down the 1. Then we move on to the next column. 0 plus 1. We get 1. We write it down. Then we move on to the other column. Remember, we move from the least significant side to the most significant side bit or digits. So 1 plus 0 gives us 1. Now, ordinarily, in decimal number system, 9 plus 5 is equals to 14. But my dear students and the rest of the learners, when you add 1, 0, 0, 1 to 0, 1, 0, 1, what we end up getting is 1, 1, 1, 0. We know very well that this is an invalid BCD number because our result has already exceeded 9. Our result has already exceeded 9. So what did we do? Because 1, 1, 1, 0 is not a valid BCD number, then we proceed. We add 6 to validate it. So we add the binary equivalence of decimal number 6 to our answer. And that is, we add 0, 1, 1, 0 to our result. Which gives us 0 plus 0 is 0. Then 1 plus 1 is 0, carry 1. So we carry 1, we add 1 to 1, we get 0, carry 1. 0 carry 1 plus 1 is 1, carry 1. We down 1, we carry 1. 1 plus 1 that we have carried gives us 0 carry 1. So 0 carry 1 plus 0 gives us 0 carry 1. Therefore, we carry 1 and we drop it down and we write it down on the most significant bit side. But because we are talking about binary coded decimal, which is supposed to be in pairs of 4 bits each, then we add 3 zeros on the most significant side to 1. So we have 0, 0, 0, 1, 0, 1, 0, 0. Remember in BCD, as I said in my part 1 of this series of presentations, we don't usually read, for example, 14 as 14. Is 1 4. So in BCD, we are supposed to present, or the result we are going to get after addition, it's supposed to reflect each of the digits separately. For example, 1 is supposed to be represented using its own binary equivalence, and 4. So in this case, after we have added 6, we have validated the BCD number we had gotten, the BCD result. Because now we have 0, 0, 0, 1 representing our 1, and 0, 1, 0, 0 representing 4. Note, my dear students and the rest of the learners, those who might have not listened to part 1 of this series of presentations in this topic, when you are given a number, for example, 14, and you are told to represent it in BCD, you simply separate those numbers, 1 and 4. And then write each of them in their binary equivalence. So you have binary equivalence of 1 in decimal, which in this case will be 0, 0, 0, 1. Then the binary equivalence of 4 in BCD will be 0, 1, 0, 0. But when we add them directly, 1, 0, 0, 1 for 9 plus 5, which is 0, 1, 0, 1, the answer that we got, in fact, was not giving us the result as required in BCD. That's why we had to validate it by adding 6. And therefore, the result we have gotten is now a valid BCD number. So our answer becomes 0, 0, 0, 1, 0, 1, 0, 0. For clear understanding, my dear students, on how we deal with BCD, kindly visit Emily Swap ICT YouTube channel and listen to part 1 of 3 in this series of presentations. So our answer becomes 0, 0, 0, 1, 0, 1, 0, 0 binary. Here is another example. Add the following BCD numbers and state if they are valid or invalid BCD numbers. The first one is 23 plus 15. Number 2, 19 plus 14. My dear students and the rest of the learners, I would like you to pause this presentation, then work out these two examples. Once you are through, you can click or tap on this presentation so that you can proceed and see whether you have gotten it right or not. So our solution becomes 23. We write it as 23. That is 0, 0, 1, 0 to represent the 2, and 0, 0, 1, 1, which is binary equivalence of 3. And then we are adding it to 15, so to 1, 5. So the binary equivalence of 1 is 0, 0, 0, 1. Binary equivalence of 5 is 0, 1, 0, 1 in BCD. So we add each of them. When we add 1 plus 1, that is, I am adding, or you start adding from the least significant side. So 1 plus 1 is 0, carry 1. That carry 1 plus 1 gives us 0, carry 1. 0 carry 1 plus 0, we get 0, carry 1. So we move that 1 to the next column. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. So we write 0, we carry 1. 1 plus 0 is 1. 1 plus 0 is 1. We down 1. Then we move on to the next column, which is 0 plus 1. That gives us 1. We write 1. Then we move on, we add 1 to 0. That gives us 1. Then 0 plus 0 is 0, and 0 plus 0 is 0. So we get 0, 0, 1, 1, 1, 0, 0, 0. My dear students and the rest of the learners, if you look at 0, 0, 1, 1 is 1, 1. Binary 1, 1 equals to 3 in decimal. What about is 1, 0, 0, 0 binary equivalent to 8? If yes, then what you have gotten is a valid BCD result. And it's true. The binary equivalence of 3 is 1, 1. And because it's in BCD, we include 2 zeros on the most significant side. So 0, 0, 1, 1 is equals to 3. It's equivalent to 3. While 1, 0, 0, 0 is equivalent to 8. So that is a valid BCD number. So as long as each pair of binaries equals to the required decimal equivalent, and what you get does not exceed 9, then, or the value you get does not, the decimal you get does, or the decimal number you get does not exceed digit 9, then you have a valid BCD number. So our answer becomes 0, 0, 1, 1, 1, 0, 0, 0 binary. Let's look at the other one. We have 19. So we write it as 1, 9 in the following order. We write the binary equivalence of 1. That is 0, 0, 0, 1. Then the binary equivalence of 9. It is 1, 0, 0, 1. My dear students and the rest of the learners, if you're wondering how we are arriving at these binaries, it is simply because you have not listened to part 2 of 3 in this series of presentations. And therefore, I advise that if you're wondering where we are getting the zeros and ones from, kindly visit Emily Swap ICT YouTube channel and listen to the video on binary, or in other words, access the video by the title, Data Representation in the Computer, Part 2 of 3 in this series of presentations on number systems conversions. And it is also important you also listen to part 1 for the introduction. Then we add to 14. We get 1. The binary equivalence of 1 is 0, 0, 0, 1 in BCD. The binary equivalence of 4 is 0, 1, 0, 0. So we organize them as I have done. Then you add each pair of binary. So what do we get? 1 plus 0 is 1. 0 plus 0 is 0. We write down 0. 0 plus 1 is 1. We write down 1. Then 1 plus 0 is 1. We write down 1. 1 plus 1 is 0 carry 1. We write 0, we carry 1. 1 plus 0 is 1. 1 plus 0 is 1. We write down 1. Then we move on to the next column. We add 0 plus 0, we get 0. 0 plus 0, we get 0. And therefore, our answer becomes 0, 0, 1, 0, 1, 1, 0, 1. So, for us to know whether this is a valid or an invalid BCD, we look at each of the pairs of binary and we see whether, or we ask ourselves whether each pair is equivalent to its respective decimal number. So a 0, 0, 1, 0, the equivalence a binary for 3 decimal is 1, 1, 0, 1. Equivalence binary, is it a binary that is equivalent to decimal number 3? By the look straight, we can see it is not, because the binary equivalence of 3 should remain as 3 from both the pairs. But this is not the case. So straight away, this one is not valid. However, for us to know whether it is valid or not valid, we convert this binary, each pair, to its decimal equivalent. What does it give us? If you convert 1, 1, 0, 1 to its decimal equivalent, you will not get 3. You will not get 3. So, what do we do to make this number a valid BCD? So we add 6 to 8, the decimal equivalent of binaries of decimal 6, the binary equivalence of decimal 6. This gives 0, 1, 1, 0. So we add 6 to this BCD. When we add 6, what we get is 1 plus 0 is 1. Write down 1. 0 plus 1 is 1. Write down 1. 1 plus 1 is 0, carry 1. Write down 0, carry 1. 1 plus 1 is 0, carry 1. So 0, carry 1 plus 0. We get 0. We carry 1. 1 plus 0 is 1. We down 1. And then we drop down the other bits. All we assume that we have some zeros. And we then add 1 plus 0 gives us 1. 0 plus 0 is 0. 0 plus 0 is 0. What I am saying, my dear students and the rest of the learners, is this, that because there is nothing here, once you have added 1 to this 0 here, you get 1. You write it down here. Then because there is nothing here, you can assume that what you have below here is zeros. And therefore, 1 plus 0 gives us 1. 0 plus 0 gives us 0. Then 0 plus 0 gives us 0. That's what I'm saying. So after adding, we ask ourselves, is 0, 0, 1, 1 the binary equivalence of these 3? Is 0, 0, 1, 1 binary equivalence of these 3? So what you do, just convert 0, 0, 1, 1 back to its decimal equivalent and see whether you get 3. Then do the same for the other pair. See whether you get 3. If you get 3 in both the cases, then our BCD will be correct. So after converting, I have gotten 3, 3. And therefore, this is now a valid BCD number. Because each pair of 4 binaries or 4 binary digits is equivalent to each binary or each decimal in our value. 19 plus 14 is 33. So 3, 3. So the first pair of 0, 0, 1, 1 is equivalent to 3 in decimal. The other pair, 0, 0, 1, 1 is equivalent to 3. So that is a valid BCD number. So we write our answer as 0, 0, 1, 1, 0, 0, 1, 1 in binary. Let's now look at 2's complement addition. 2's complement addition. 2's complement allows arithmetic to be implemented very efficiently in hardware and allows for detection of arithmetic errors, such as overflow. Overflow occurs whenever the result of an arithmetic operation is bigger than the work area. For example, if the result is to be stored in an 8-bit work area or register, and the result generates more than 8 bits, then an overflow occurs. So, what are the rules for addition in 2's complement? Number 1, start by adding the 2 numbers. Observe carries into and out of the sign bit. Then, if there are no carries involving the sign bit, the sum is correct. If there is just one carry involving the sign bit, the sum is incorrect because of overflow. That is, the sum is too large to be represented correctly by the computer. Overflow occurs only when we are adding two positive or two negative numbers. So we ignore the carries out of the sign bit when evaluating the sum. Let's now look at binary subtraction. 2's complement can also help us deal with the subtraction of binary numbers. My dear students and the rest of the learners, note that I am still under the 2's complement, but I would like you to understand that using 2's complement, we can perform various operations such as binary subtraction. And that's why I am introducing the aspect of binary subtraction under the 2's complement, because 2's complement can help us deal with the subtraction of binary numbers. There are 4 main rules to be adhered to when subtracting 2 binary numbers. These rules are: number 1, 0 minus 0 gives us 0. The second rule, 1 in binary minus 1 in binary, in other words, 1 minus 1 gives us 0. Rule number 3, 1 minus 0 gives us 1. Number 4, 0 carry 1 minus 1 gives us 1. Simply, you read it as follows. Borrow 1 from the next most significant digit. In other words, when you are subtracting 1 from 0 carry 1, or in other words, if you are subtracting 1 from 1, 0 in binary, what you do is, because 0 is less than 1, we borrow 1 from the next most significant digit to make 0 become 0 carry 1, or you can say 1, 0 in binary. Hence, 1, 0 minus 1 gives us 1. Remember, if you add 1 plus 1, it gives you 0 carry 1. But because we are subtracting, we now borrow 1 from the next most significant digit, which is 1. We add it to 0. That gives us 1. And therefore, what we get is 1, 0. When you subtract 1 from it, we get 1. Simply, my dear students and the rest of the learners, always remember as a rule that 0 carry 1 minus 1 gives us 1. Or you can also read it as 1, 0 in binary minus 1 in binary gives us 1 in binary. So the three main methods, of subtracting binary numbers are 1, using direct method or normal method of subtraction, or using 1's complement, or using 2's complement. So we have direct method subtraction, 1's complement subtraction, and 2's complement subtractions. Let's look at how we use direct subtraction methods. The steps are as follows. Number 1, work out the binary subtraction, or here's an example to assist you be able to know how we move on with indirect subtraction. So if, for example, you are told, work out binary subtraction of 1, 0, 1, 0 from 1, 1, 0, 1. In other words, if you are told subtract 1, 0, 1, 0 from 1, 1, 0, 1 without being told anything else, what do you do? My dear students and the rest of the learners, I would advise that you pause this presentation, work out this calculation, and then tap again on the presentation to proceed so that you can see whether you have gotten it right or not. So this is what you do. Get your first number, which is 1101. Subtract 1010 from it. So you organize them in this order, in the order of their significance. So 1 minus 0 is 1. 0 minus 1, you find that 0 is less than 1. So we carry 1, or we borrow 1 from the other column, the value which is immediate to our 0 on the most significant side, that is on its left side. So 1, we borrow 1 from 1. So 1 plus 0, or in other words, let me put it nicely, my dear students and the rest of the learners. I repeat, 1 minus 0 gives us 1. But because 0 is less than 1 and we want to subtract 1 from 0, we borrow 1 from the left hand side, and that's from the most significant bit. So we get 0 carry 1. So 0 carry 1 minus 1 gives us 1. 0 carry 1 minus 1 gives us 1. So we write 1. Then we move on to the next column. We already borrowed the one which we can see here. We already borrowed this one. And therefore, what we have here is 0. So 0 minus 0 gives us 0. Then 1 minus 1 gives us 0. And therefore, our answer becomes 1, 1 in binary. Let's now work out the other calculation, which is we subtract 1100 from 10011 in binary. So what do we do? When we subtract directly, we can see 1 minus 0 gives us what? It gives us 1. 1 minus 0 gives us 1. Then 1 minus 0 is also equals to 1. Then 0 minus 1. So we can subtract 1 from 0. So we borrow 1 from here. But then this is also a 0. So we move on to the next digit, which is 1. So we borrow 1 from this one here. So when we borrow 1 from here, we bring it here. It becomes 0, carry 1. Then we carry that 1 again. We borrow our 1 again. We borrow 1 from this 0, carry 1. We bring it here. And therefore, 1 plus 0 gives us 1. 1 minus 1 will give us a 0. Then on the next level here, we have a 0. So we already borrowed, or we carried, or we borrowed 1 from here and we brought it here. But now we have another 1 which is remaining, and therefore we borrow again 1. So we have 0 I repeat this calculation, my dear students and the rest of the learners, for ease of understanding. I repeat this explanation, my dear students and the rest of the learners, for ease of understanding. We repeat, we have 1, 0, 0, 1, 1 minus 1, 1, 0, 0. This one. So 1 minus 0, we get 1. This one. Then 1 minus 0, we get 1. This one. And then 0 minus 1. 0 minus 1, we can subtract 1 from 0. So we borrow 1 from this column. So we borrow 1. But here also we see that 1, or that here we have 0. So we borrow 1 again from here. So we borrow 1 from here, we bring it here. Then we borrow 1 from this column, we bring it here. So here we have 1 carry 1. 1 carry 1 minus 1 gives us what? According to the rules of binary subtraction, 1 carry 1, that is 1 carry 0 minus 1 should give us a 1, not a 0. Did you notice this, my dear students and the rest of the learners? I repeat, when you add or when you borrow 1 and then you bring it to this level here, it becomes 0 carry 1. So 0 carry 1 minus 1, it gives us 1. And of course we know that 1 plus 1 is equal to 0 carry 1. So we add our 1 here. Then we move on to the next column. Here we brought 1, or we had borrowed 1 from this level. We brought it here. So what remains here is a 1. So here we have a 1 at this point here. So 1 minus 1 will give us a 0. Then we borrowed this 1. So what is remaining here is a 0. So 1 minus 0 minus a 0 will give us a 0. And therefore, our answer becomes 0, 0, 1, 1, 1. So our answer becomes 0, 1, 1, 1 binary. My dear students and the rest of the learners, we now proceed to the next level. Let's now subtract or carry out subtraction using 1's complement. We are through with the indirect method. Let's now work out subtraction using 1's complement. So subtraction of binary numbers using the 1's complement allows us to subtract using addition. The main purpose of using the 1's complement in computers is to perform binary subtractions. So to subtract x from y, in other words, if you have two numbers and you want to subtract the minute from the subtrahend, then number 1, you should determine the 1's complement of the minute. That is the number that you are subtracting from another. The number you are subtracting from another is what is called minute. And the number from where you are subtracting from is the subtrahend. So the first step is to determine the 1's complement of the minute. The number you are subtracting from another number. Number 2, you add 1's complement of the minute to the subtrahend. In this case, my minute is x and my subtrahend is y. Number 3, remove the carry and add it to the result. This is called end around the carry, EAC. Here is an example. If you are told to subtract 1, 0, 0, 1, 1 from 1, 1, 0, 1 using 1's complement method, you should note that the minute in this case is 1, 0, 0, 1, 1. The subtrahend is 1, 1, 0, 0, 1. So how do we proceed? My dear student, as usual, pause this presentation, work out this computation, and then click again on this presentation to proceed so that you can assess your answer. This is how we proceed. Get the 1's complement of 1, 0, 0, 1, 1. The 1's complement, just as I have said in this presentation, when you are getting or working out 1's complement of a binary, you change or you convert 1's to zeros and zeros to 1 or to 1's. So you alternate the values, or you change the values. So we get 0, 1, 1, 0, 0. Then add the ones complement. In other words, add what you have gotten to the subtrahend. So add it to 1, 1, 0, 0, 1. So we add them as we have done. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0 carry 1. So we write 0, we carry 1. 1 plus 1 is 0 carry 1. So 0 carry 1 plus 0 is 0 carry 1. So we write down the 0, we carry 1. We drop down the 1. And we write now our answer or our result as 1, 0, 0, 1, 0, 1. Now, from this computation, you can see we are dealing with 5 bits for subtrahend and 5 bits for the minute. But now we have generated a carry. We have forwarded, or we have, after doing our addition, after adding our most significant bits, 1 plus 1, we have gotten the 0 carry 1. 0 carry 1 plus 0, we have seen it is 0 carry 1. So if you carry 1 as our last action, then that 1 is what we are calling end around carry. So what do? We add that carry. So we add that carry to our digit or our number or our value that we have gotten. So we pick that carry, and in this case is 1. We add it back to the value we have already gotten. So what do we get? 1 plus 1 is 0, carry 1. So we write down 0, we carry 1. 1 plus 0 is 1. So we write down 1. Then we drop down the other values. Why? We assume that what we have here are zeros. So we proceed. 1 plus 0 is 1. Then 0 plus 0 is 0. Then the other one is 0 plus 0 is 0. So we get 0, 0, 1, 1, 0. And therefore, the result is 0, 0, 1, 1, 0, binary. So that's how we proceed, my dear students and the rest of the learners. What about if you want to subtract a smaller number from a larger number using the ones complement method? If you are subtracting a smaller number from a larger number using the ones complement method, you proceed as follows. Number 1, determine the ones complement of the number being subtracted. Then add the ones complement to the larger number. From there, remove the final carriage and add it to the results. For example, if you want to subtract 1101. Binary from 1001. What do you do? So in the case you want to subtract a large number from a smaller number using one's complement, do the following. Number one, determine the one's complement of the large number. So in this case, of course, we know that our large number is 1101 and our smaller number is 1001. And we are subtracting the larger number 1101 from the smaller number 1001. So after we have done that, the next step is add the ones complement to the smaller number. If there is no carry, the result will have a positive sign from the answer. And this will be the ones complement of the answer. So step number one, determine the ones complement of the large number. Secondly, add the ones complement to the smaller number. You realize that there is no carry because you are subtracting. So the result will have a positive sign from the answer, and this will be the ones complement of the answer. From there, you change the sign and take one's complement of the results to get the final answer. Let's see with an example. If you are told to subtract 1101 from 1001 by using one's complement, what do you do? My dear students and the rest of the learners, pause this presentation, then work out on this calculation, and then once you are through, click or tap on this presentation to proceed so that you can assess your performance. So, my dear students and the rest of the learners, this is what you do. So our solution will be, number one, we compute the ones complement of 1101. That is the ones complement of our large number. That is the number that we are subtracting from the smaller number. So the ones complement of 1101 is 0010. We change ones to zeros and zeros to ones. Secondly, we now add the ones complement, that is the number, the answer we have gotten, to 1001 as follows. So 1 plus 0 gives us 1. 0 plus 1 is 1. Then 0 plus 0 is 0. 1 plus 0 is 1. So we get 1, 0, 1, 1. And therefore, what we now do in step 3 is we change the sign. So how do we change the sign? If what we have as the most significant bit is a 1, we change it to 0. If it was a 0, we change it to 1. So in this case, we change 1 to 0. So it becomes 0, 0, 1, 1 binary. Then we take now 1's complement of 0, 0, 1, 1, which gives us 1, 1, 0, 0 binary. So, my dear students and the rest of the learners, that is simply how we subtract a large number from a smaller number using the complement that we have already discussed. That is, using 1's complement. Here is another example. Find the value of 9 minus 6 using 8-bit 1's complement. Find the value of 9 minus 6 using 8-bit 1's complement. If you are given such a question, what do you do? So we proceed as follows. Number 1, rewrite the problem as 9 plus minus 6 to show that the computer performs binary subtraction by adding the binary equivalent of 9 to the 1's complement of 6. Remember, computer performs binary subtraction by adding the binary equivalence. Computer performs binary subtraction through addition. That's what I mean. So to show that the computer performs binary subtraction by adding the binary equivalence of the various digits or numbers, then you need to rewrite the problem, in our case, as 9 base 10, that is 9 in decimal, plus minus 6 in decimal. Number 2, convert the absolute value of 6 into 8-bit equivalent. That is 0, 0, 0, 0, 0, 1, 1, 0. So that is our 8-bit equivalent of 6. Number 3, take the 1's equivalent or the 1's complement. Take the 1's complement of 0, 0, 0, 0, 0, 1, 1, 0. The 1's complement of 0, 0, 0, 0, 0, 1, 1, 0 is 1, 1, 1, 1, 1, 0, 0, 1 in binary, which is the binary representation of -6. Note that our most significant bit in this case is 1. It is 1. So that 1 indicates that it is a negative number. Then add the binary equivalent of 9 to 1's complement of 6. That is 0, 0, 0, 0, 1, 0, 0, 1. We add the 2, 1, 1, 1, 1, 1, 0, 0, 1 that we have already gotten. So what do we get? 1 plus 1 is 0, carry 1. Write down 0, carry 1. 1 plus 0 is 1. 1 plus 0 is 1. Write down 1. Then 0 plus 0 is 0. 1 plus 1 is 1, carry 1. In other words, let me repeat. 1 plus 1 is 0, carry 1. So we write down our 0. We carry 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 0 is 1. Plus 1 is 0, carry 1. We carry 1. 1 plus 0 is 1. 1 plus 1 is 0. We carry 1. And because there's no any other value up there, we write our 1 at that point. So you have seen that we have carried, or we have generated a carry in our last step. So we have gotten carry 1. So that 1 that we have carried and written at our last step, that is what we have called and around the carry. So pick that 1 and add it to the result. So remove it, remove that carry from where it is and add it to the result. So that gives us 0 plus 1 is 1. So the rest of the digits, we bring them down, excluding the carry because we have already removed the carry from its position. So we get 0, 0, 0, 0, 0, 0, 1, 1. So the answer becomes 0, 0, 0, 0, 0, 0, 1, 1 in binary. And of course, in the real sense, 9 minus 6 is 3. The binary equivalence of 3 is usually 1, 1. And because we are talking about 8-bit representation, then we have 0, 0, 0, 0, 0, 0, 1, 1 in binary. Let's now look at how we subtract using 2's complement. Subtraction using the 2's complement is done by forming the 2's complement of the minute and adding it to the subtrahend. Thus, the usual AND operation is used to subtract. Like in 1's complement, the 2's complement of a number is obtained by negating a positive number to its negative counterpart. To subtract a smaller number from a larger number using 2's complement, proceed as follows. Number 1, convert the smaller number to 1's complement. Then add the 1's complement of smaller number to 1. Then add the results you get to the large number. Number 4, discard a carry if it's generated when you add the final digits. For example, if you are told to find the value of 9 minus 6 using 4-bit 2's complement binary, what do you do? Find the value of 9 minus 6 using 4-bit to complement binary. So in this case, proceed as follows. Number one, rewrite the problem as follows. 9 plus minus 6. Then convert 9 to its binary equivalence. The binary equivalence of 9 is 1, 0, 0, 1. So if you convert 9, decimal 9, to equivalent or to binary equivalent to its binary equivalence, you get binary 1, 0, 0, 1. Then to find negative 6, we need to find the 2's complement of 6. So we convert 6 to its binary equivalent. This will give us the binary equivalence of 6 is 1, 1, 0. And because we are talking about 2's complement, we make our bits to be 4, which is of course the rule of BCD. So we make them 4. So in this case, it is 0, 1, 1, 0. Then we find the 1's complement of 0, 1, 1, 0. This will give us 1, 0, 0, 1. Because the 1's complement of a number, a binary, is gotten by changing zeros to ones and ones to zeros. So that gives us 1, 0, 0, 1. Then we add 1 to get the 2's complement. So we add 1 to 1, 0, 0, 1. If you add 1, 0, 0, 1 to 1, or you add 1 to 1, 0, 0, 1, you get 1, 0, 1, 0, which is equal to negative 6. We then add 1, 0, 0, 1 and 1, 0, 1, 0. When you add the two, what do we get? So 1 plus 0 is 1. 1 or 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 0 carry 1. Because we have generated a carry, which is 1, we discard this bit. We discard this bit. Why? Because it is a carry. So bit 1 is discarded because we are using 4 bits. The answer is therefore 0, 0, 1, 1 binary. To subtract a large number from a smaller number using the 2's complement, we do as follows. Number 1, we determine the 1's complement of the large number. And then we add 1 to the 1's complement value. Number 3, we add the results to the smaller number. Then we discard the carry. So you discard the carry for your results. Let's see an example. Subtract 1, 0, 1, 0, 1 from 0, 0, 0, 1, 0 using 2's complement. This is how you proceed, my dear students and the rest of the learners. Kindly work out this computation before you see how I am solving this problem. And therefore, as usual, pause this presentation, work out on your problem, and then press or tap on this video or this presentation to proceed once you are through. So our solution is, number 1, we get the 1's complement of 1, 0, 1, 0, 1. And that gives us, from my previous demonstrations and examples, it will give us 0, 1, 0, 1, 0, because we change 1s to zeros and 0s to 1s. Then from there, we add 1 to our 1's complement. So we add 1 to 0, 1, 0, 1, 0. This gives us 0, 1, 0, 1, 1 in binary. The third step is we add the 2's complement to 0, 0, 0, 1, 0. Therefore, we add 0, 1, 0, 1, 1 to 0, 0, 0, 1, 0. That gives us 1. So 0, 0 plus 1 gives us 1. We write down 1. 1 plus 1 is 0, carry 1. So we write down the 0, we carry 1. 1 plus 0 is 1. 1 plus 0 is 1. We write down 1. So 0 plus 1 is 1. We write down 1. 0 plus 0 is 0. We write down 0. So our answer is 0, or our result is 0, 1, 1, 0, 1. And therefore, our final answer becomes 0, 1, 1, 0, 1 binary. Here is a question, my dear students and the rest of the learners, that I would like you to work on to assess your understanding to what we have learned. The question is, find the value of 109 or 109 minus 60 using 8-bit 2's complement. Find the value of 109 minus 60 using 8-bit 2's complement. Pause this presentation, work out this operation, and then once you are through, you tap to proceed. So, have you done this, my dear students and the rest of the learners? This is how you are supposed to perform such a computation. Number 1, rewrite the problem as 109 plus bracket minus 60, and convert 109 and 60 to binary. So when you convert 109 decimal to its binary equivalence using long division method, you continuously divide 109 by 2, generating remainders until you get the last value as 1 or a 0. So in this case, 3 divided by 2 is 1 remainder 1. Because we have gotten 1 as our last value, we pick it as a remainder, and therefore, following the arrow, as I have shown, pick the series of remainders as your binary. So in this case, we get 1, 1, 0, 1, 1, 0, 1 in binary. Then convert 60 to its binary equivalent, which gives us 1, 1, 1, 1, 0, 0 binary. Then from there, you now proceed. Make both bits to be 8 by adding zeros. And therefore, for 109, we have 7 bits. That is 1, 1, 0, 1, 1, 0, 1. So add an extra bit on the most significant side. Then for 60, we have 6 bits. So add 2 zeros on the most significant side. So that gives us 0, 1, 1, 0, 1, 1, 0, 1, and 0, 0, 1, 1, 1, 1, 0, 0. From there, we get 2's complement of 0, 0, 1, 1, 1, 1, 0, 0 as follows. So convert 0, 0, 1, 1, 1, 1, 0, 0 to its 1's complement, which gives us 1, 1, 0, 0, 0, 0, 1, 1. Then add 1 to 8 to get its 2's complement, which gives us 1, 1, 0, 0, 0, 1, 0, 0. From there, and 1, 1, 0, 0, 0, 1, 0, 0, that is what you have gotten as the 2's complement, 2, 0, 1, 1, 0, 1, 1, 0, 1 as follows. So just as we have added before, you just add those numbers from the least significant side to the most significant side. So that gives us 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0 carry 1. So we lay down 0 carry 1. 1 plus 1 is 0 carry 1. 0 carry 1 plus 0 is 0. We carry 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0 carry 1. So we write 0, we carry 1. 1 plus 0 is 1. 1 plus 1 gives us 0 carry 1. So we write 0, we carry 1, and we drop that 1 as the most significant digit. So we discard this extra bit because already we have a series of 8 bits. So in this case, we have gotten 1, 0, 0, 1, 1, 0, 0, 0, 1, which are 9 bits. So we discard the extra bit, the 9th bit, this bit, 1. And therefore our answer becomes 0, 0, 1, 1, 0, 0, 0, 1 in binary. Let's now look at what we call binary multiplication. This is done by converting both numbers to positive numbers, ignoring the sign bit. That is, work with the magnitude only. The multiplication is then carried out as in normal decimal. The correct sign for the product is added after multiplication is completed. The product usually requires twice as many digits as the multiplier or the multiplicand. For example, if you are told to multiply positive 6 by negative 5 in 4-bit 2's complement, yielding an 8-bit product, you proceed as follows. Number 1, convert both the multiplicand, that is positive 6, and the multiplier, that is positive 5, into binary. So the binary equivalence of 6 is 110. The binary equivalence of 5 is 101. Then multiply the binaries just as it's done for decimals, as follows. So we just multiply the way we multiply ordinarily. That is, multiply 1 times 0, you then note the value, 1 times 1, 1 times 1, as you note down the values. Then move on to the next level, 0 times 0, 0 times 1, 0 times 1, as you write down the values. Then multiply 1 times 0, then 1 times 1, 1 times 1. Just as normal multiplication. So 1 times 1, 1, 0, we get 1, 1, 0. 0 times 1, 1, 0, we get 0, 0, 0. Then 1 times 0, 1, 1, or 1, 1, 0 times 1, we get 1, 1, 0. When we add them, we get 0, 1, 1, 1, 1. Computers can only add two numbers at a time. So, in the case you are multiplying more than two numbers, multiply the first two, then continue multiplying the result with the next number until you have multiplied all the numbers. So, number 3, our question requires the final answer to be an 8-bit. So, from the answer we get, we need to add 3 zeros to the result gotten after multiplication. In other words, because we have gotten our answer as 1, 1, 1, 1, 0, but the question requires them to be 8 bits, it means we add 3 zeros on the most significant side of our answer. That is 0, 0, 0. We add those bits to 1, 1, 1, 1, 0, which gives us 0, 0, 0, 1, 1, 1, 1, 0 in binary. Then determine the correct sign of the product and convert to 2's complement if the sign is negative. So, in our case, because among the numbers being multiplied, one has a positive sign, that is positive 6, while the other has a negative sign, which is negative 5, the expected product has a negative sign. Because 6 times minus 5, it gives us negative 30. So a positive number times a negative number gives us a negative number. A positive number times a negative number gives us a negative number. So our product will have a negative sign. Therefore, because our product has a negative sign, you should convert it to 2's complement as follows. So when you look at our result, we have gotten 0, 0, 0, 1, 1, 1, 1, 0. So we need to convert that to its 2's complement. So step number 1, we get its 1's complement by alternating the 0's to 1's and the 1's to 0's. That gives us 1, 1, 1, 0, 0, 0, 0, 1. That is the 1's complement for 0, 0, 0, 1, 1, 1, 1, 0. Then we add 1 to the 1's complement. So we add 1 to 1, 1, 1, 0, 0, 0, 0, 1. And what we get, my dear students, and the rest of the learners, when you add these numbers, you get 1, 1, 1, 0, 0, 0, 1, 0. Therefore, the answer becomes 1, 1, 1, 0, 0, 0, 1, 0 in binary. And that, my dear students and the rest of the learners, is equal to negative 30 in decimal. What about binary division? How do we go about it? For binary division, it is done by using the magnitude part only and following normal division for decimals. I repeat, binary division is done by using the magnitude part only and following normal decimal division, and the side bit is handled later. This means that you convert the numbers to their binary equivalents, and then you divide the binary just in the same way as you do for decimal numbers. Just in the same way that you do for decimal numbers. That is normal division. For example, if you are told to divide positive 35 by negative 5, this is what you do. The first step, convert 35 and 5 to binary. In this case, the binary equivalence of 35 is 1, 0, 0, 0, 1, 1, or the binary equivalence of 5 is 1, 0, 1, respectively. Then divide 1, 0, 0, 0, 1, 1 by 1, 0, 1 using the normal division as follows. So 1, 0, 0, 0, 1, 1 divided by 5, by 1, 1. We go by 1. So just the same way we divide, we place 1 on top up there. 1 times 1, 1 is 1, 1. We drop it down there. Then we subtract. When we subtract, we get 1, 1. We drop down 1 of the ones. Then we go 1. 1 times 1, 1 is 1, 0, 1. So we write 1, 0, 1 there. And then we subtract. When we subtract, we get 0, 1. So we drop down the other 1 from up there. We get 1, 0, 1. We go another 1 up there. 1 times 1, 0, 1. We get 1, 0, 1. We subtract. 1, 0, 1 minus 1, 0, 1. We get 0, 0, 0. And therefore, we pick our values up there. That is 1, 1, 1 in binary. Then determine the correct sign of the quotient. If it's positive, the answer would remain as 1, 1, 1. But because the sign of the quotient in this case is negative, and just the answer 1, 1, 1 by forming its 2's complement. That is, the 1's complement of 1, 1, 1 is 0, 0, 0. Add 1 to the complement to make it 2's complement. That is 0, 0, 0 plus 1. We get 0, 0, 1. Then add 1 in front of the most significant bit for the sign bit. That is, or our answer becomes, or our result becomes 1, 0, 0, 1. And therefore, our final answer becomes 1, 0, 0, 1 in binary. And that, my dear students and the rest of the learners, is equals to -7 in decimal. Congratulations for learning part 3 of 3 of this presentation. We have therefore come to the end of the series of presentations on the topic data representation in the computer. Congratulations, therefore, for learning part 3 of the topic on data representation in the computer. You can access part 1 and part 2 of the series, as well as other topics in computer or ICT field by clicking or tapping on Emily Swap ICT YouTube channel below this video. You can also subscribe to this channel by tapping on subscribe button below this video if it's not currently reading as subscribed. You can also visit and subscribe to Emily Swap Life Skills YouTube channel for free life skills, motivational and inspirational resources. For any further correspondence, kindly write it to us through the email emilyswap@gmail.com. Thank you very much for listening to me, and God bless.